Hello everyone, I'm Lukas Westphal, Ingredients Research Team Lead at Camden BI, and I would like to use the opportunity of this brief video to give you some insights into the research that is being done at Camden to study the potential of ingredients to replace egg in food products. Replacing eggs in food products is a hot topic at the moment, and this trend has a variety of drivers, starting with significant fluctuations in the global egg supply and pricing, and many manufacturers within the UK will have probably experienced some disturbance after Brexit this year, because a large proportion of powdered egg products are imported from Europe. Other reasons for taking eggs out of your formulation could be down to increasing safety concerns or the resulting reputation damage from the 2017 contamination scandal that involved the insecticide fipronil, or simply due to the fact that egg is one of the major allergens in foods. Overall, the demand for egg replacement products is also a result of the move toward plant-based diets in our population, and manufacturers have significantly increased their efforts to deliver sustainable products that meet these increasingly complex consumer expectations. Replacing egg, however, is not a straightforward job because egg is one of the most versatile and functional ingredients that we have available. While delivering a protein of very high nutritional quality, the egg white proteins ovalbumin and ovomucin are well known for their ability to create stable foams that are needed for a lot of food products. The egg yolk, on the other hand, can provide color and serve as an emulsifier due to the natural occurring lecithin. There are a range of other functions and benefits that eggs have in foods, starting with its ability to coagulate from around 60 degrees Celsius, and therefore it's contributing to the texture and mouthfeel of a lot of food products. Since egg replacement is so high in demand currently, there are a range of egg replacers available on the market, and many of these consist of multiple ingredients. Often used are potato starch, tapioca starch, different proteins from milk, pea, chickpea, or sunflower seeds, but also hydrocolloids like xanthan gum or methyl cellulose or other forms of cellulose can commonly be found in these products. From our member-funded research project on plant proteins, we wanted to take a closer look at pea proteins and study the differences of various pea protein products and how well they perform in a fatless sponge cake formulation. For the purpose of our studies, we have used what we call a lean control recipe, which contains only relatively few ingredients. You can see the ingredients here in the table on the left-hand side. So we used an equal amount of heat-treated flour and sugar, 19% egg, based on the total recipe weight, 15.2% water, and small levels of baking powder and emulsifier paste. And you can see on the right-hand side here what this control cake looked like. At the beginning of our experiments, we looked at 8 different commercially available pea proteins, and we based the level of addition of pea protein for each one on the solid level of egg in our control cake formulation. As we know that proteins can vary significantly in their water absorption, we assessed the water holding capacity of all studied pea proteins and adjusted the liquid levels based on these results to maintain butter viscosity, but also to give each protein an equal chance to perform well in this formulation. You can see in the table here that the water holding capacity between these 8 proteins varied from 223% to 293%. From the initial baking trials that we did, one protein that stood out was pea protein number 8, which was one of those with a lower water holding capacity of 223%. However, rather than the water absorption of this protein, it was actually the better flavor, or probably more accurately, the lack of off flavors that made this protein stand out in comparison to some of the other tested pea proteins. As you can see on the image here though, the product was far away from perfect, being slightly lower in volume and also showing some large tunnels throughout the cake, particularly on the outer edges here of the product. So, in order to improve the product characteristics further, we have created 4 additional versions of this recipe, optimizing the water and emulsifier level and adjust the butter viscosity. The graph here shows the butter density on the y-axis, here in grams per milliliter for all cakes made during the study. At the bottom, you can see the different proteins. For protein 1 to protein 7, we only have one recipe, and for protein 8, we have all the different versions shown on the graph. Firstly now, looking at all the unmodified recipes of pea protein number 1 to number 8, we can see that all pea proteins have significantly increased the butter density, meaning that all cakes will have less air incorporated in comparison to our control sitting at a density of around 0.65 grams per milliliter. The modifications done to pea protein number 8 version 5 has decreased the butter density from close to 0.8 to around 0.75, but it is still significantly higher than the control formulation. This graph here now shows the specific volume of the baked cakes in milliliter per gram. Firstly, we can see that the control cake shown at the very right-hand side of the graph was significantly higher in specific volumes than all other cakes, with a specific volume of 3.19 milliliters per gram. The highest specific volume achieved with unmodified pea protein recipes was 2.08 with sample 6 or 2.07 with sample 8. The modifications made to pea protein 8 allowed a significant improvement of specific volume to 2.44 in recipe version 3 and 2.39 in recipe version 5. Apart from volume, texture is also an important quality characteristic that influences consumer acceptability. To measure the textural properties of our cakes, we have used a Stable Microsystems texture analyzer and performed a texture profile analysis on the crumb of our cakes at the points shown in the sketch here at the left-hand side of this graph. All tests shown here were performed on the day after production. The two cakes that showed the lowest hardness values were the two modified recipes of pea protein 8, version 3 with 645 grams and version 5 with 606 grams. Although neither of the cakes achieved the same low hardness that the control cake showed, it is important to note that a lower specific volume of a product, which we have seen with all protein cakes, will in most cases result in a harder product due to the resulting higher density. When looking at texture firmness, the moisture content of the crumb is another very important parameter because an increased level of moistness within the crumb can simulate a softer crumb, which may come at the expense of other textural imperfections. From the moisture analysis shown in the graph here, however, we can see that the modified versions 3, 4, and 5 of pea protein 8 are all very similar to the control cake at around 30 to 31% moisture content. While moisture content is an interesting parameter in relation to textural characteristics, the water activity of cakes is a more important factor when considering their shelf life. On this graph here, we have mapped the water activity of all cakes, and our control cake is placed on the left-hand side here of the graph with a water activity of around 0.88. Which would, without the use of preservative, give our control cake a mold-free shelf life of at least 6 days when stored at 21 degrees Celsius. Many of the pea proteins showed a significant increased water activity, up to values of around 0.92 for pea protein 4, which would essentially halve the mold-free shelf life of the control cake. The modified versions of pea protein 8, with the exception of recipe version 3, all show water activities comparable or even lower than our control, which means that these would not reduce the mold-free shelf life of our cakes, but in the case of recipe version 2, could even increase the shelf life by 3 additional days. However, thinking back to the graphs I showed earlier for the moisture and texture, we could also see that this recipe had the lowest amount of moisture present and resulted in a significant increase in hardness. It was actually the hardest of all cakes made. From all the analysis we have conducted, we came to the conclusion that our pea protein 8 recipe version 5 has produced the best cake out of all tested proteins. When looking at the two images here, we can clearly see the improvements that the adjustments of water and emulsifier level have made. Recipe version 5 at the bottom shows an improved volume and structure versus the starting recipe with all large tunnels essentially disappeared from the structure. Comparing this protein formulation now to our control recipe, we can see that the crumb structure of the pea protein cake looks even finer than the control formulation. However, the pea protein cake slightly lacks volume and its color is slightly different to our control, which however could be accounted for by further recipe adjustment and the use of colorings. To summarize, we have seen quite significant differences between different pea proteins. Differences were especially significant in regards to their flavor and water absorption capacity. Lastly, we have shown that plant proteins can be used as effective ingredients to mimic some functionality of eggs in sponge cakes, but it has also become clear that further recipe modifications are required in order to achieve optimum properties. Thank you all very much for listening. If you have any further questions relating to this study, our member-funded research project on plant proteins, or other activities relating to baking or ingredients research, please get in touch. My contact details are shown here on the screen, or visit our website at camdenbri.co.uk.